Okay, so good morning. It's a pleasure to have Dario Rosa here visiting us today. So Dario did his master's in the University of Genova in Italy, then his PhD at the University of Milano Bicocca. Then he spent quite a while in South Korea in many different institutions. So SNU, KIAS, KAIST, and IBS, if I got it correctly. Then he came to Brazil, in particular to São Paulo, and he was in ICTP for a while. And now he's a professor at IFT, UNESP.
From next week.
Okay, starting next week. And, well, he works with quantum many-body physics, focusing on quantum chaos, thermalization, many-body localization, and applications in quantum technologies. So today he will talk a little bit about his ongoing work. So Dario, thank you for being here, and the stage is yours.
Yeah, thanks a lot for the invitation. No, now it's on, yeah. So it's really great to be here. It's the first time in Natal, and I enjoy the natureza. It's beautiful, yeah. So the title of the talk is a bit weird, probably. Krylov and chords somewhere over the rainbow. So I think I will pass most of the talk in explaining the various terms, in explaining what I mean by Krylov, what I mean by chords, and what I mean by the rainbow. This is based on an ongoing work with one of our postdocs in ICTP Safer, Debargia Chakraborty, which we are confident will appear next week. So if you like the talk, stay tuned and check archive, because probably will appear next week. So let's start with an idea of what will be the story of this talk in a nutshell. So suppose that you are in a place and you have your refrigerator here with a block of ice inside, the door is closed, and okay, everything is in equilibrium. Then you, or could be me, I do that often, you go, you take something from the refrigerator, you forgot the door open. And so you can imagine what is going to happen. Well, it's going to happen that the ice got melted and you remain with just water. So if the talk was just that, would have been probably pretty boring, right? You just see something that is going to be melted. However, what I try to convince you today will going to happen is that if you wait long enough, but not too long, a finite amount of time, you will see that your block of ice is going to rebuild and going to be back. So here the question becomes that definitely something weird is going on. We don't expect that when we are in front of a refrigerator, and we want to understand what's the fate of thermalization in this case. So this is more or less what we are going to discuss, of course, without ice and without a refrigerator. We will discuss this in a quantum many-body systems, but more or less the philosophy will be exactly this. We will have an equilibrium state that follow the rules of thermalization, thermalize and become, in this case, water, but then something happen and recast in the original form. By the way, interrupt at any time with questions and so on. Maybe we can make the talk more entertaining for everybody. Okay, so this is more or less the outline. So I was told that this talk is supposed to be somehow close to a colloquium. So I will start really by something simple, and I will start by recalling what do we mean by thermalization in the quantum regime and how we understand for a closed quantum many-body system the thermalization process, and this will require us to introduce the notion of eigenstate thermalization hypothesis. Then actually we will focus on how we can escape from ETH, and then we will focus on the phenomenon of quantum many-body scars. And we will describe that in quantum many-body scar physics, we can have revivals due to that. And then we will go to the actual content of the talk, which is how we can build the scars in bipartite system, and we will introduce our rainbow state, so the first word. Then we will see a Krylov-inspired construction for a tower of many-body scars, and so we will see the second word in the title. And then this will, up to here, the construction will be general. Then we will go to a specific construction, let's say to a particular example. We will discuss how this machinery can be applied in the double scaling limit of the SYK, and we will see how we can avoid thermalization in this setup. And then we will do some conclusion. By the way, the last word, chords, will enter here. So far, so good. So let's start a little bit by recalling the classical setup. So we know that in classical system, typically thermalization is discussed in the framework of the ergodic hypothesis, that in a nutshell tell us that in the long run, our system will visit all the possible microstate. It looks, is it work? Yeah. Will visit all the possible microstates with equal probability. This is the ergodic hypothesis that somehow is at the base of our understanding of thermalization. So this ensures what I call weak thermalization. By that I mean the following: ensure that if I evaluate the time evolution of a certain observable, the average over the time evolution, so I take the limit for t going to infinity of the integral of OT of O x and p of t over the entire evolution, this average value, exactly because the ergodic hypothesis, will be equal to the let's say microcanonical average over all the possible allowed configuration of O, and so will be equal to the thermal value by definition. So essentially, the ergodic hypothesis per se ensure that after a long time, the observable will reach the thermal value on average. However, there are two problems with this that we don't see that let's say they are at odds with our usual experience. The drawbacks are the following. First of all, long time is required. You need to wait that your system has enough time to explore the full phase space. And this, if you have a many-body system, will make the time necessary for thermalization astronomically large. And this is not what we see. We thermalize in finite time. Normally, if we leave our block of ice out of the fridge, this will not need an infinite amount of time. We'll thermalize much easier. Second, and in a sense even more important, we are talking about average thermalization. So that means that using only this point of view, we cannot exclude large fluctuations. So in principle, we should expect that at a certain moment, our block of ice rebuild again and become another block of ice and then go back again. Is not what we see, of course. So let's say the ergodic hypothesis, of course, is correct, but we need something else, right? What do we need? Well, the drawbacks can be cured by introducing the notion of typical configurations, which essentially tell us, this is the whole point of statistical physics, tell us that if I consider relevant observables, and okay, here we can be a bit sketchy about what we mean by relevant, but let's say something that can be measured at the thermodynamic level, at the macroscopic level, something like that, we know that the various microstates can be grouped, and most of them will form typical configurations. So this, in other words, gives us an idea that probably the phase space will look something like this. We will have our phase space that can be, let's say, tiled in islands, all of them forming a typical configuration, all of them forming, let's say, a set of typical configurations that, from the point of view of a of a macroscopic observables, they are all equivalent to each other. And then there will be other places which are atypical, which are, let's say, the configurations to which we start. We start our evolution from an atypical configuration, and we do evolution. So why this solve the previous drawbacks? First of all, because now the relevant time scale is not anymore the time scale necessary to explore the full phase space. Become the time scale necessary to move from an atypical, from a non-equilibrium configuration into one possible typical configurations. Once we are there, we are thermalized. Moreover, let's say, ensure that we don't have only weak thermalization that I introduced before, but we have strong thermalization. which means once we are in a typicality island, all the various configurations are equivalent, and so we remain in that, let's say, macro state for a long time. And so we don't see huge fluctuations of the various observables. Okay? So this is, let's say, how we thermalize in the classical setup. We have, of course, the ergodic hypothesis, but more than that, we have the notion of typical configurations that somehow work as a basin of attraction for all the possible configurations, and that ensure strong thermalization. So remember, strong thermalization means that you don't have to make a long time average to reach a thermal value. Good, we want to go to quantum. So we want to see how quantum mechanics ensure thermalization. By the way, when I say quantum mechanics, I always mean closed systems. If you go to open quantum systems, there are other ways in which you can thermalize, because you have a neat bath or a reservoir, so things change. But here everything will be done at the closed level. So remember a little bit the ingredients that we will have in this game. So we have a many-body Hilbert space, of course. So suppose that we have n particles. Most of the time will be qubits, but not necessarily. So our Hilbert space will be just the tensor product of the single particle Hilbert spaces that I put here. Then another ingredient is the initial state. So we will start with the vector, or better, array in the Hilbert space, size 0. And then the third important ingredient is, of course, the Hamiltonian. The Hamiltonian that give us a spectral decomposition, so these are our energy eigenstates. And the Hamiltonian provide us the notion of time evolution, because we know that the time evolving operator is simply the exponential of the Hamiltonian. Here we don't need to, I would say in the entire talk, we will deal with time independent Hamiltonian. So the time evolution is simply the exponential of the matrix. And this will give us the evolved state. However, the Hamiltonian give us also another important concept in this game, which are the thermal and the microcanonical states, which means anytime I have my quantum many-body, in this case Hamiltonian, I have two sets of important, for thermalization, states. The first is the thermal state, that roughly speaking is the exponential of minus beta, where beta is the inverse temperature H. And the second one is a microcanonical state around a certain target energy E bar. So this form a microcanonical state that is a microcanonical shell. So the Hamiltonian give us a notion of thermal or thermodynamically these two are equivalent. So give us a notion of a thermal state. So now we want to see how we can formulate thermalization in the quantum regime. This is actually a very old problem. I think it was addressed at the very early days of quantum mechanics by von Neumann, essentially. So it's a very old subject. And let's see what was the von Neumann insight. So let's be really layman's, and let's go with the wrong approach. The easiest and wrong approach would be to say, well, I want that in the long time, for t going to infinity, my psi of t will approach a microcanonical state at energy E bar, or will approach a thermal state at inverse temperature beta. Why this is a wrong approach? Do we have students that we can tease? Yeah, let's see the students. Do you have an idea why this is definitely a bad idea? The question is, let's assume that I want to introduce a notion of thermalization, saying my system thermalize if, starting from an initial state, after enough time, I approach a microcanonical or a thermal state. Why this is definitely not a good idea? Very good. So this is absolutely incompatible with the rules of quantum mechanics, because the quantum mechanical rules are unitarity, and so you cannot reach a mixture starting from a pure state. Notice, this is why I was emphasizing we are in a closed setup. If we are in an open setup, we have the possibility to actually reach a thermal state by time evolution, because evolution is not unitary anymore, but this is incompatible. So this in principle would say, well, you never thermalize, you never reach a thermal state. The insight of von Neumann was to realize that we should, in a sense, exactly like in classical systems, we should think about thermalization as a process that is reached by the expectation value of reasonable, in this case local, observables, not by the states. So what really reach the thermal equilibrium are the expectation values and not the states. So entering in this mindset, we can again introduce a notion of weak and strong thermalization. We can, at the weak level, ask that the average of the expectation value of our state approach, this time, the expectation value of the same observable in the thermal or the microcanonical state, and this is the weak thermalization. At the strong level, we can ask that after a certain finite, possibly, thermalization time, our expectation value will stay close enough to the expectation value of the thermal state in the same with the same observable. And we want this to be quote unquote generic. So we want that this process doesn't depend on the specific choice of the observable or on the specific choice of the initial state that I take. We want that this is a sort of generic. There are no mathematicians here, right? So I can forget about details like what do I mean by the generic and so on. But we understand each other, right? Okay, great. Okay, now let's see the problem, how we can try to attack this problem. So we have these two notions of thermalization. We can, since in both cases appear this expectation value, we can think about studying this expectation value. Well, here we have a microcanonical shell, so makes sense to study this expectation value in the energy basis. So I introduce my energy basis, En, that I already introduced. My psi t becomes simply this, where psi 0 was just the Cn, the probability to write anywhere. So the expectation value take a time independent part when the two matrix when the matrix element is diagonal, and then an oscillating part with the off-diagonal elements. And so we want to see how we can reach thermalization within this framework. People have worked quite a lot on that, and I think in the late 90s, something like that, Deutsch and Schrednicki came out with an ansatz called eigenstate thermalization hypothesis that essentially tells us that the thermalization properties of a given Hamiltonian lives in the eigenstates of the same Hamiltonian. So this is an ansatz, and by the way, I think it's still, let's say, this is what we're going to describe is a mechanism that ensure thermalization. I would say there is absolutely no proof that this is the only one. There might be other particular systems that still thermalize without obeying the ansatz that we're going to describe. I think this is technically an open problem. But anyway, I would say all the systems that we know thermalize via the ETH. So it's a robust phenomenon. So as I said, the ETH ansatz is an ansatz on the matrix elements of the observables. So on the matrix elements between the eigenstates of the many-body Hamiltonian and the observable that we are studying. This is the ansatz. So he's saying us that the matrix element ONM, of course, can be split in diagonal part, delta NM, and off-diagonal part. And this characterize, okay, let me introduce two quantities, E bar, that is the mean energy between N and M, and omega, that is the energy difference between N and M. So the ansatz is telling us that, let's say, the diagonal part is controlled by a smooth function of the energy, of the mean energy between N and M. This is important. Is a smooth function, depend only on the mean energy, and this function is exactly the same, give exactly the same value of the expectation value of O computed in a microcanonical state centered around E bar. So this is telling us that essentially there are no changing, let's say, I take N n equal to, let's say, 10, and then I take n equal to 11, the matrix element O 10, 10 and O 11, 11 will be essentially the same. This is what I mean by this is a smooth function just of the energy, and is controlled by the macrocanonical value. Then what about the off-diagonal elements? Well, the off-diagonal elements are they look like pseudo-random numbers, so we don't make any prediction on them. They look random. Of course, they cannot be random because they are controlled by the Hamiltonian, but superficially they look random. But the most important thing is that they are exponentially suppressed in the energy. So they are extremely suppressed, extremely small compared to the diagonal contribution. So here is an example in which I'm plotting. I'm not. I copied from somewhere, but anyway, in which we are plotting O and M for various. Probably I would say the absolute value of O and M for all the possible for a choice of an observable and for all the possible N and M of a certain finite dimensional many-body system. And what we see indeed is that along the diagonal there are larger values and they are quite homogeneous. And when I move out from the diagonal, there are huge suppression, and essentially the matrix elements are almost zero in magnitude. This you can show. It's a very simple exercise. You can show that the first term, ensure weak thermalization. So ensure that if I take the time average after long time of this guy will cancel, and this guy will bring me to the microcanonical value that I wanted. So will give me weak thermalization. The second term is important for strong thermalization because it kills the time fluctuations and bring me fast to the thermal value. So the two terms combined ensure strong thermalization in total. Questions, comments, complaints?
Also time-dependent parts, so they are not important for
No, the time-dependent part is entirely, I'm assuming that the Hamiltonian is time-independent. I'm assuming that the observable is time-independent, so the matrix elements will be time-independent. The time-dependent part is here. Sorry. Is here. Depends on the state, on the evolution of the state. And essentially, what you can do with a simple exercise is that these fluctuations are... let's say this contribution is exponentially suppressed given that the matrix element is exponentially suppressed, and so the fluctuations become exponentially suppressed, and so they're not visible. Okay, so let's see some consequences of ETH that we will use later. So, as I said, in the ETH ansatz, thermalization is encoded in the eigenstates of the Hamiltonian, so we expect that the eigenstates will share some common feature due to their thermalizing properties. People have studied that, and they find indeed that, again, they look thermal state for local observables, so they cannot be thermal because, as you said, time evolution, or let's say no, they cannot be thermal simply because they are pure state by definition. So they must have correlations, but these correlations are extremely non-local, such that if you probe them with a local observable, you don't see that correlation, and they look thermal states. The second one, again, they look similar to random states. So suppose that these are the components of the eigenstate. The probability distribution of them is essentially a delta function, so they look completely random, and this actually provides a beautiful connection between ETH and random matrix theory that we will not discuss. Finally, they are highly entangled. They show a volume law entanglement in which essentially the entanglement entropy for a bipartition sit in a curve like that, and they are highly entangled. Good. Now, let's introduce, let's say, a diagnostic of thermalization that we will use in the talk. So, of course, as I said, since the dynamics is unitary, the information about the initial state cannot be lost, so it must be transferred toward non-local degrees of freedom because the local one lose this information. So in some sense, this is why, in some sense, thermalization is bad, because suppose that you prepare your state in which you put your information nicely put local such that you can recover, and then you let it evolve. Information is still there, but become non-local, essentially not achievable in any way. So this is why sometimes we think that thermalization is bad. Now, let me introduce a diagnostic of thermalization that we will use in the talk, that is the return probability, which is, as the name suggests, is the probability. We start from an initial state, and we measure the probability at the time t that we measure again the initial state, so this overlap. And of course, ETH and thermalization imply that if t is larger than the thermalization time, the probability of observing again the same state will become super small. If that is the case, we have thermalized. So this will be somehow the diagnostic that we will use later to discuss how we escape from thermalization. As I said, thermalization is sometimes unwanted because you effectively lose all your information. So again, suppose that I prepare a state I want to send to my friend such that he or she can do something important with that. If there is thermalization in between, the state becomes completely useless. So there are cases in which we want to escape from thermalization, and people have devised ways to escape from thermalization. The first one are integrable systems. They have an extensive number of conserved quantities, and so they don't thermalize because they have to preserve all these conserved quantities in involution. However, this is not what people really love in condensed matter. Somebody has an idea why integrable systems are not that nice for people in condensed matter? Who is the right person? Him. Yeah. Yeah, Rodrigo. Yeah. Well, I don't know. Maybe you can confirm or not. So maybe you can disprove. But I think they are not that nice because they are extremely fragile. So as soon as you perturb a little bit your system, the integrable structure is lost, and you are back with the thermalization. So let's say, suppose that you want to build a system that escapes from thermalization. If you base your approach on an integrable system, then your experimental friend has to suffer dramatically in order to create such a system, because a tiny perturbation will destroy everything. Do you agree? He's not a good person. Okay. Anyway, then people have thought about other mechanisms, and they came out with disorder. The famous Anderson model is an example in which disorder, although it's single particle, in which disorder prevents thermalization. In that case, thermalization, since it's single particle, is probably not, let's say, prevents from diffusion. So disorder is a mechanism, and then people are still arguing right now if Anderson localization is or not a stable mechanism in the many-body setup. These two approaches are all cases in which we have a strong breaking of ETH, in the sense that the spectrum as a whole will violate ETH. People, and this will be the focus of today, has also developed other mechanisms, many-body scarce, that we will call weak breaking of ETH. So we will have a system that as a whole is thermalizing, but for some specific initial condition, we can escape from thermalization. This is a weak mechanism of breaking of thermalization because you don't destroy the thermalizing property of the entire system, but you develop subsector of the systems that escape from thermalization. Question, comments, complaints? Yeah.
Anderson localization is not a thermal state, or
No, well, come on. I'm not saying that it's not promising since I work on that, but let's say the fact that Anderson localization is a robust phenomenon in the large system size limit is established for the Anderson model that is single particle. So you have to assume that your electrons don't interact, which is a fishy assumption. If you introduce interaction and you start to talk about many-body localization, people are still arguing if many-body localization is a genuine phase of matter in the thermodynamic limit, or is just a transient, or is just... I'm not saying that is a bad mechanism. I'm just saying that there are people still arguing if many-body localization really exists as a real escape from thermalization or not. But let's say...
So yeah, my doubt is, why is it at all a mechanism of escape in thermalization? Why it cannot be... why it cannot be localized and thermalized?
Why cannot be localized
at the same time? Because you said it's a mechanism to avoid thermalization.
Well, because essentially the only way to study many-body localization, I would say right now, is by exact numerics. And if you are extremely good in numerics, you can go to, let's say, 22, 24, 26 spins, you see that at that level there is a critical disorder after which the eigenstates seems chaotic, but you see, for instance, that the critical disorder to reach such a non-thermalizing behavior is growing with the system size. So you don't know. I mean, 26 spins are not many, right? So suppose that you want to study a piece of metal, you have an Avogadro number, and then making prediction about the large n limit with the numerics that goes up to 26 is tough. Yeah, so again, I'm not denying that is a topic that should be studied. I'm saying that there are still debates about that. Yeah. Okay. Anyway, the focus of today will be many-body scars, so let's introduce what they are. So let's introduce via an explicit model the PXP that has been the first one introduced by Zlatko, Papic, Turner, and others. So this is a system of L qubits. So the local Hilbert space is just empty or full, or let's say down or up. And we will consider these two operators. X is the spin flip, so it changes from up to down and vice versa. And then we will have also P, which is the projector on the down spin. The Hamiltonian that we are going to consider is this, in which we have two projectors in I-1 and I that sandwich the spin flip in I. And so this realized a constrained dynamics, because essentially you can flip this spin only if the other two are already down. So for example, this transition is possible. This transition is not possible, will be killed by the Hamiltonian. So this relies a constrained dynamics. You don't do freely the spin flip, you do it only depending on the states of the other. And introduce also another notion that is relevant in scar physics, that is the notion of Hilbert space fragmentation. So for instance, suppose that you have a certain configuration with two up spins. It's a simple exercise. By applying this Hamiltonian, you see that these two spins cannot be moved. They will remain there forever. They are frozen. So this introduces some dynamical fragmentation in the Hilbert space, because, for instance, these two states that have exactly the same number of excitations, 2, so they would look like to stay in the same sector of the Hilbert space, they are actually dynamically separated, because this configuration will be never able to go there, because these two spins will be always up. So this introduced an extra, let's say, a sort of extra conserved quantity, which cannot be written as a standard conserved quantity, but introduce this fragmentation. Great. So what do they do in this paper, Zlatko and friends? So they consider it a set of initial states, ZK, that are a family of states in which you do an alternating up, down, but you separate two up by K downs. So Z2 is really up, down, up, down, up, down. Z3 is up, down, down, up, down, and so on. These are product states, so in particular they are states that are relatively easy to prepare in a lab. If you have a cold atom system, you can probably set up this as an initial state, and you let them evolve. Let's see what happened at the level of the return probability. This is what they observe. They observe that for D equal to 4, so for Z4, so up, down, 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 up, and so on. So for a state prepared in this way, the return probability immediately goes to 0 and remain there. So this is a signal that our system is thermalizing. But if you start from Z2 and Z3, you see huge revivals in the return probability. This is a signal that thermalization for these states is not happening. Why? Okay, this is exactly what I said. So we have a system in which we have a weak violation of ETH, because the vast majority actually of the initial states thermalize, but we can induce non-thermalization for some special states. Why? You can study the Hamiltonian spectrum, and what they found was the following. Here they compute the entanglement entropy for a generic bipartition of my full spectrum, and they observe that the vast majority of the spectrum is actually thermalizing, is sitting in this high entanglement setup. But there are few states that are outlier. They are non-thermal. They don't go to the volume law prediction, and they are also almost equally spaced in energy. So they form a special sector in the full Hilbert space that has these low entanglement properties, and they are also equally spaced in energy. Then what they do is to study the overlap of your initial state Z2 with all the possible states, all the possible eigenstates of the Hamiltonian. What they observe is that this initial state Z2 has a huge overlap with the special eigenstates here. So now these two facts combined explain why Z2 doesn't thermalize, because it's effectively living in a subportion of the Hilbert space, which are equally spaced, of states that are equally spaced in energy. So of course they will show finite time revivals simply because after a time, I wrote it here. So the mechanism is now clear. We have a thermalizing Hamiltonian with few atypical states that are equally spaced almost in energy delta E. So if you can find a reasonable initial state psi 0 that have large overlap with this atypical state, this psi 0 will be forced to have revivals with a period proportional to 1 over delta E. So this is how you break thermalization in this setup. You have a question?
Why is it important to be equally spaced?
Because this is what you need. The time evolution creates. You know, the time evolution is. And so you want a common device or something like that, common multiplier here, such that you reconstruct a full period for all of them. So must be that they are equally separated in energy. Okay, now, okay, yeah, let's say. Now, let's think about that. Suppose that I have a certain spectrum that goes from minus E to plus E, and this is my entanglement entropy stuff. Well, in principle, you could say, well, I can do for every system, I simply pick one state here, one state here, one state here, that are more or less equally spaced. So an initial state having huge overlap with this finite portion of it will show revival. So what is generic, what is special of this? It seems to be a rather generic mechanism. The point is that if you take few eigenstates that are volume low and you try to create a state having overlap with only them, you will end up with an initial state that will be an horrible crocodile that will be essentially impossible to build in a lab. The fact that these states are low entanglement ensure that a state having overlap with most of them will be a low entanglement state, or in this case even a product state. So if you want, the fact that you can create finite time revivals with a fine-tuned initial state is not a super special phenomenon. What is really special is that you can do that with a state that is low entanglement, or in any case that is a reasonable state. It doesn't look a strange state, so to say. Good. So what are we going to do now? Because so far I explained things that have been done by others. So let's see what we did actually. So we introduce a general construction that you can use in bipartite system to build many-body cars. And we will show that in this construction, you have a bipartite system, so you have your...
Hello. So
please.
Before going on, so if I have an initial state which has like very high overlap with those low entanglement states, which like more or less with equal energy spacing, how robust it is if I change a little bit like the energy splitting, like I put a delta?
Okay, yeah, you can see here if you want. If they were exactly equally spaced, these revivals would have been exact, would have been 1. The fact that they actually decreases but slowly is exactly because, so let's say you will still see revivals, but they will die in the long time.
I see.
Okay, so here we will consider two systems, left and right. So that's why the system is bipartite. And essentially in these constructions, we will see that we can build many body cars, and moreover, we will see that the states that do revivals are not low entanglement states, but they are still interesting because they will be equilibrium states for the left systems. So we will have a bipartite system. Once you observe the bipartite system from the left point of view, you will have equilibrium states that under the dynamic only of the left system will be equilibrium, so will not evolve. Due somehow to the dissipation, so to the interaction between the two systems, these equilibrium states will show revivals, and this will be the equivalent of the block of ice put in a fridge, let it open, because the block of ice is an equilibrium state for the fridge, but due to the interaction with the environment, will do an evolution, but this evolution will be non-thermal and will do revivals. So this is what we are going to see with this construction. Good. I'm repeating, so we have two halves of the system, the left and the right, NL and R, both equal to N. So we have, once again, a local Hilbert space HI, each of them is dimension D, and the total Hilbert space is HL tensor HR with the dimension D to the 2N. We will consider a given, but somehow generic, I would say rather generic, Hamiltonian only living on the left system. So this is an operator that sends the left Hilbert space to the left Hilbert space with this decomposition. This is incorrect. It's not up to n. It's up to d to the n, of course. But okay. And this is the crux of the entire point. In the full system, we will start with the fully anti-correlated Hamiltonian. So we will say that the full Hamiltonian will be the H that we introduced before, tensor the identity in the right system, minus, and the minus is crucial, I tensor the same Hamiltonian. So we have exactly the same Hamiltonians living on the left and on the right with a minus sign in between. This is fine-tuned. I have to admit, it's a fine-tuned construction, but still. So now the question is, can we break ETH starting from this setup? To do that, we need to start from the rainbow state. So now it's clear why I'm talking about rainbow in the title, the rainbow state. So we observe that in the total Hamiltonian, in the full spectrum, there is a there is a sort of special eigenstate, the rainbow state, which is simply the sum of all the E tensor E for the two Hamiltonian. So I take all the possible energy eigenstates and I do the tensor with the same energy eigenstate and I sum all of them. And it is a zero energy, so in particular a very highly excited state because the spectrum goes from minus to plus, so it's really at the center of the spectrum, eigenstate. Now this state is pretty interesting because it's an infinite temperature thermophile double state, which means that if I take this state and I look it from the left point of view, so if I do the partial trace over the right system, what I got is a mixture including all the eigenstates with equal weight, so including a thermal state at beta equal to 0, the infinite temperature. Moreover, and this is something that was shown by Thomas Iadecola, Langlet, and collaborators in this paper, it has a very atypical entanglement spectrum in the sense that the correlation between the left and the right, if you do a bipartition of this kind, in which you bipartite half of the left and half of the right, you will get a state that in this bipartition will have zero entanglement. So it's atypical because it has a very atypical entanglement structure. Fine. However, we know this is a scar. It's a scar because it's atypical. It has an atypical entanglement structure, so it's a scar state. That is one. So the dynamics will never see that. It's impossible dynamically to see the effect of this state. So the question is, can we extend the framework and have a tower of equally spaced scars? We will do that, and we will do it in few steps. The first step is to consider the following subspace that I call H Krylov. So the second word is now out, Krylov, which is the span in which I take my thermophile double 0, and I consider all the possible actions, all the possible powers of HL acting on that. This is the Krylov subspace of the Hilbert space that we will focus on. it is clear, it's a super simple exercise, that this form an invariant subspace. So all the states living here are actually zero energy eigenstate of the full Hamiltonian. And there are notable members in this subspace. For example, all the possible thermophile double for every possible inverse temperature beta, they live here. So in this subspace, there are interesting states that are formed by all the possible thermophile double, which, seen from the point of view of the left system, are thermal states. No, for every choice of beta. For every choice of beta, you have a thermophile double at another inverse temperature, and it lives there. So let's say all the thermal states, let me say in different words, all the thermal states of the left system, when they are purified to the right system, they live into this subspace. Still, we notice that H. Krylov contains interesting states, but they are non-dynamical, so the model is very boring. They are all zero energy eigenstates. So can we deform the model to get some non-trivial but non-ergodic dynamics? Here I will present one strategy, that is the counting operator strategy. So suppose that I can find an operator n that satisfies these two requirements. The first one is that when restricted to H. Krylov, this operator n become an endomorphism. That means that whenever I act on a state living in H. Krylov, I get another state living in H. Krylov. This is the first requirement. So if I can find an operator that restricted give me an endomorphism, so such that I can define the operator n0, which is the restriction of n acting on H Krylov. The second one, suppose that n0 is a counting operator, so its spectrum can be split in n such that all the eigenvalues are put in correspondence with natural numbers, up to maybe a multiplicative constant, but more or less. So now, suppose that I have these two. It's clear that the Hamiltonian H mu, the full Hamiltonian plus mu times n, could induce a non-ergodic dynamic in H. Krylov, because somehow what it does, could do, is to split the H. Krylov space that initially was a zero energy space, so pretty boring, can split in rooms with various values of n. This will create new dynamics inside H. Krylov. So suppose that I can do that. Now the question is, okay, do we have an example for that, or you're just talking? Okay. Let's say that the very construction, the very definition of H. Krylov suggests a counting operator. What we can do is to take our span, do a Gram-Schmidt, we get a set of orthogonal eigenstates ordered, 0, 1, blah, blah, blah. So we can say, well, our n0 is simply this operator. This, of course, will induce a set of eigenstates, so all the H. Krylov get spanned by eigenstates that are equally spaced in energy, and they are immersed in the full Hilbert space. This will create a non-ergodic dynamic for all the states living in H. Krylov. And so, in particular, we can already see that if this is the case, if I can realize this structure, any state living in H. Krylov, that can be written as here, will have finite time revivals with a revival period that will be exactly 2 pi over mu. So I will have revival dynamics for every state living in H. Krylov. Even more, if I consider these two quantities, the energy measured by the left system and the commutator between n0 and h0, I can see that their time evolution satisfy an harmonic oscillator algebra, do exactly that. So we will see that from the point of view of the left system, every state living in H. Krylov behave like a state that give energy to the environment and get back energy again to the from the environment, because its energy measured in the left system show a oscillatory dynamics. This is exactly like the block of ice that I started with. What is the problem? The problem is that the states n are obtained via an orthonormalization procedure. So these states will be in general some weird state. So it's possible, without further clues, that this operator n0 will be a complete mess. And once you try to rewrite in terms of the microscopic fields, microscopic operators, this operator will be an horrible beast, which probably is not the easiest way to, again, to go to an experimentalist and say, look, prepare this operator. Probably they will be not very happy. So in general, this construction is robust, is mathematically correct, useful, probably not much. So the question that probably the referee would have asked if we don't do the next part would say, well, but can we find reasonable realization of these constructions, or we are just playing? What we know so far, finding necessary and sufficient conditions for the existence of a reasonable n0 is an open problem. I don't know the answer. What I can describe now in the last 10 minutes is an explicit but approximate construction based on the SYK model. Good, so let's go fast, let's say, with the SYK model, because I assume that many people already know everything. So we know that an SYK model is an all-to-all model for n Majorana fermions, so operators that satisfy this kind of anti-commutation algebra. They can be taught as linear combination of creation and annihilation operator for fermions. They are described by an Hamiltonian that is all-to-all, and it is Gaussian, it is disordered, and the disorder is Gaussianly distributed. This is a very nice model for many reasons. For instance, the model is solvable in certain sense in the larger limit, and it is known that for p equal to 4 or higher is highly interacting and thermalizing. There is an extra limit, which is the limit in which n goes to infinity and p also goes to infinity. So the number of fermions interacting all together goes also to infinity in such a way that 2p squared over n is finite. This is called the double scaling limit. In this limit, the model becomes even more solvable. There are extra algebraic structures that can be used to constrain the dynamics. So what we will do is to show something in this limit and then numerically show that what we got in this limit is robust outside of this limit. We can do the last part only numerically because we don't have the analytical tools. Good. So what is the bipartite SYK model? Well, of course, it's, let's say, the same. We have the left Majorana, the right Majorana. We take a left SYK, a right SYK with exactly the same disorder. So fine tune, I have to admit a bit. And then we need an interaction term. We start with this operator S that is called size operator, that can be written apart from an additive constant that is not that important, can be written as the product of all the pairs psi j L, psi j R. Now, a little bit of algebra show that this is a counting operator, and in particular, the ground state is a positive operator by construction, given this. And the ground state of this operator is the rainbow state, the infinite temperature thermofield double state. And all the excited eigenstates can be put in correspondence with a string of Majoranas, left Majoranas, all of them different from each other, so this, acting on the rainbow state. Whenever I take a string of Majoranas of length S, this state will have eigenstate equal to eigenvalue equal to S under the action of the S operator. Okay, now we need to settle a little bit down. We built a counting operator, and our goal was to build another counting operator. So we want to see how this counting operator is related to the counting operator of the Gram-Schmidt procedure that I described to begin with. So the question is S counting what we want to count, or is counting something different? Well, let's see. As I said, S counts the length of the fermionic string built on top of the rainbow state. So we have the rainbow state, that is the ground state. Then we have a set of dimension n of eigenvalue 1 states that are all the psi I left acting on 0. Then we have n choose 2 excited states, and so on and so forth. On the other hand, the operator n0 comes out from a Krylov construction. So the idea is that we start exactly from the same state. Then we consider the state 1 is the state in which 0 is acted upon by a single copy of HL. The state 2 is acting on HL on 1 and removing the part that bring me back to 0. This is the orthonormalization part. And these states in the SYK literature are called the chord states because they can be put in relation with some chord diagrams, and you can use this diagrammatic technique to work with that. So what we have to do is to compare these two beasts. We see that the pattern start to emerge. So the ground state is exactly the same. The first excited state here is actually one particular representative of a state that from the point of view of S is living in the eigenspace P, because acting with HL, I created P Majoranas, so is one representative, because it's a linear combination, of an eigenstate living in the state P. The thing becomes complicated with starting with 2, because 2, since there are also contractions between two copies of HL, can be written as a state living in 2P for the operator S plus corrections. So now, can we make it precise, the relationship between the two operators? The answer is yes, and actually was already done for different reasons by Henry Lee a few years ago. You can compute on a generic chord state, which is your target, you can compute the expectation value of the S operator and the variance. And what we see is that the operation value, the expectation value of S grows with P, while the variance remain fixed with P in the double scaling limit. So that means, this again was shown for different reasons by Henry Lee, that S can be written in first as an approximate macroscopic realization of the Krylov operator. You can say that N0, your target, is actually P times S approximately, plus corrections. That become better and better in the double scaling limit. So in the double scaling limit, it follows that every state in H Krylov will show non-ergodic dynamics, finite revivals, energy oscillations, and so on. Now, let me conclude. The double scaling limit is not the most suitable limit, right? I mean, if you go to a lab and you ask your friend again, I want an infinite number of Majoranas that interact with an infinite number of members at the same time, such that the infinite square divided by the infinite remain finite, they will not do the experiment. So let's see. Already doing experiment with SYK is a mess. Imagine to do an experiment involving also this extra feature. So the question is, are the revivals visible at finite N and finite P? Let's see what we can expect. So let's say this relationship is telling us that the equivalence between N0 and S is more pronounced for chord states with low n. So we expect that for chord states with large n, the difference between S and N will be highly visible. For chord states with low n, the difference will be not that visible. So among the states in H Krylov, we expect the states with large overlaps with the low-lying modes of N0 will probably show better revival dynamics, while states having large overlap with the large N chord states probably will not show very large revivals. Among these states, we have all the thermophile double states at large temperatures. So we can expect that they will show a good revival dynamics, a good non-ergodic dynamics. We didn't have any other way. What we did was to do finite 10 numerics. So we took 32 Majoranas in total, 16 left, 16 right, a values of the coupling constant mu equal to 0.5, and three relevant choices of the initial state. The first one, the orange, is a generic state living in the full Hilbert space, not even in H Krylov, living in the full Hilbert space. Then we took a generic random state living in H Krylov, so in the large N, large P limit, this will show revival dynamics, but we'll have large overlaps with the large N chord states. And then finally, we took a finite beta thermophile double. We studied the numerical revival probability, and this is what we got. For the beta equal to 1 state, we see huge revivals that goes almost to 0, 0.1 something, and reconstruct up to almost 0.9. And notice that this line is the prediction, the double scaling limit prediction of the revival period that is amazingly satisfied. For a generic state, we see the thermalizing property of the full model. The revival probability goes to 0 and never recast. For a generic state, but in H. Krylov, that should show revival, there are actually there are not revival, but the thermalization is highly delayed. This is because, as I said, the states with low n would like to keep away from thermalization. The states with large n go to thermalization. So overall, you thermalize, but very slowly. Then, to conclude, we did a little bit of stability analysis changing mu. And what we find is that the system is extremely stable for change of mu's with the predictions that are excellently satisfied. So let's say changing mu doesn't destabilize the model. On the other hand, changing beta can make big changes. If beta is too small, we will have that our thermofield double will have a huge overlap with 0. 0 is an exact eigenstate. So essentially, the revivals will be exact, but will be very minor. This will go only up to 0.7 or something, so doesn't go really to 0. If beta is too large, the revivals will be immediately suppressed because you have overlap with large chord states. The sweet spot somehow is between 1.2, 1.5, in which essentially you go with the return probability to 0, which look thermal, but then you reconstruct quite high, up to 0.75. So let's conclude. We said that the escape from ATH is a challenging task. Many body scars are one of them. One of them example. We introduced a construction of non-ergodic dynamic in bipartite setup that pictorially look like the ice block let in the fridge open that melt and rebuild again. It's not me, right? Ah, okay, great. Probably because it's time to finish. Then we found an explicit realization in the context of the SYK model. Future possibility, as I said, we want to understand what are... No, but then it's a problem of me moving here. Okay. Yeah, I think it's... Let's try. No, yeah, let's see if it remains stable. As I said, the future possibilities are, are necessary, finding necessary and sufficient conditions for this to happen. Another, here we are doing a dynamics that, from the point of view of the left system, is moving thermal state, or let's say equilibrium state, to other equilibrium states, always remaining always in the equilibrium setup from the point of view of the left system. As somebody could know, in quantum thermodynamics, an important task is to finding shortcuts to adiabaticity, so finding ways to make an evolution that doesn't, that let's say, that is as similar as possible to the semi-static case, but is infinite time. I believe that this is a kind of mechanism that goes in that direction, because move equilibrium states to equilibrium states without generating coherences. So could have applications of that. On that. Let me conclude. Advertising the Latin American Quantum Alliance, the LAQUA. This is a website that we started to develop from a few months in ICTP Safer. It's a site that is essentially aimed to connect researchers, professionals, and other figures that are interested in the generic quantum science and technology in Latin America. We organize monthly webinars. We organize conference, or let's say we advertise conferences and workshop, job offers, or other things like that. So I invite all of you to visit the website. Here is the website. Register, and you will get the mail. It's not spam. I mean, we send an email just once every 2 weeks or something like that. So you will not be spammed by that. Okay, thanks.
Okay, let's open for questions.
When you're talking about the PXP model, you said something like it had some additional symmetries.
Yes, let's say you have a symmetry in the sense that, as I said, the states okay, let's go. I mean, as I said, suppose that you have a state like a 0, 0, 1, 1, 0, 0, 0. This state will be dynamically disconnected from any other state that doesn't have this 1, 1 here. You can do any kind of dynamics, but so you can, let's say, split the Hilbert space in chambers that are dictated where you put the, let's call it, roughly speaking, it's not a domain wall, but where you put this kind of structure. So for instance, this define a subsector of the Hilbert space that is completely decoupled from this. This define another subsector that is decoupled. So you could, working thing backwards, you could create an operator that is the symmetry. The point is that this symmetry operator is a monster that doesn't have any relationship with the standard, like particle number conservations or.
Right.
So,
yeah. My question is this among the could this be like a sufficient condition if you have these additional symmetries? Do you have revivals and scars?
I suspect it's yet to be fully described.
Is there any counterexample or?
We should have asked Tom to that, because he's one of. As far as I know, as far as I know, it's a coincidence, but I don't think the relationship between the two is fully understood. Let's say that, as far as I know, every scar system that I know, apart from this new one that we don't know, also because it's a very peculiar, you have Majoranas, so, but any other, let's say, more standard scar system that I know show Hilbert space fragmentation. That I know. I don't know.
And the sectors are labeled by some symmetry operators.
Yeah, but symmetry operators that are non-standard, like here you should.
Yeah, something beyond charge conservation or anything.
Yeah. For example, there are systems in which the sectors are labeled by the number of domain walls. So you can move a domain wall, but you cannot create a domain wall. Now, making an operator that counts the number of domain wall, create a super non-local operator that is not standard. So, yeah, in that sense.
Thanks.
So first, thanks for the great talk. So following in the Hilbert fragmentation thing, are the spaces that the Hilbert space composed into blocks actually, the dimension of each block is actually a polynomial with n?
Well, in the case, I would say this is problem dependent. You have to count. Okay. In the case of the PXP, if you stay in the largest room, the largest sector, which is the one in which there are no of these configurations, in which you never have two spins that are both up, goes like a Fibonacci n. So is smaller than exponential. That's why you can study the PXP to much larger values. But yeah, I would say that is problem dependent. It's not hard. Once you have the model and you recognize what is concerned, then is accounting stuff. But I would say it's model dependent.
Okay. So other thing, one of the plots you show the comparison with the finite n and finite p as okay with the double scaling limit. I think.
Finite n, finite. Yeah, I think you are referring more or less.
With the time around 10 or something. Yeah, this one. So for me, it's quite a little bit surprising with finite and finite p. You have such a great matching.
For me as well. That's why we're writing a paper about that.
Yeah, right.
I'm joking.
How large is p on this case?
Or how large
is p on the finite side simulation?
4.
Oh, 4. Okay.
Yeah.
And
we try to see. Okay. I mean, it's embarrassing because we try to, because this is 32, the best we could do is to go to 36 Majoranas, and the results are stable. But again, we are doing the error, we are doing the mistake of MBL. We are pretending to say something about large N.
Yeah.
So, yeah.
But like, I mean, it's already very interesting just to point out the fact
No,
that
yeah.
very
Let me also say that, let's say, in the SCAR community, okay, I don't know if I'm talking for everybody in the SCAR community, but at least for a certain subsector of the SCAR community, they don't discuss the physics of scars as a new phase of matter. So if you go out from that paradigm, the mesoscopic setup can be still interesting. If you are discussing, like in MBL, if you are discussing like I have a new phase of matter, the only thing that matter is the large N limit. If you instead are interested in mesoscopic effects, well, finite N, finite P, it's a decent, it's a fair limit. It's a fair situation. Let's say.
Right. Because I would assume that like to have such a great matching, the explanation would be something of the sort that in the blue state, like the subspace that the blue state leaves during the dynamics, is one that changes very smoothly as you grow N and P. Like it doesn't change much. You like the subspace that it leaves, like as you take the, I mean, the family of large system size NP, which is very hard to do numerically.
Okay.
Is like wouldn't change, like this curve would like not change much.
Well, let's say I think you are kind of right, because if you want, this vertical line is actually computed using the double scaling limit, and is actually very nicely satisfied. So that suggests that, yeah, probably the dynamics is robust, but I don't want to commit too much.
Right, yeah.
Okay, yeah.
Thanks.
Okay, more questions? Oh, if not, let's thank Dario again.
Thanks.